I readjusted a little bit. Realized once I looked at that video that I was standing mostly off camera most of the time. That's all right. As I was saying right at the end, in space, outer space, there is no, sound waves cannot propagate because there is no matter. There is no matter to compress. There are no air particles to get packed close together, and there are no air molecules that will then become rarefied, become more spaced out than normal. There are no particles in outer space. So sound waves cannot propagate because the pressure waves don't ever exist. So that is why there is no sound in space. I'm good with that? Let's go on to important features of waves. Should be able to fly right through these. Important features of waves. Firstly, amplitude, word that came up last, unit. Okay, means basically the same thing here. The amplitude, and it means the same thing that it did in math, is the height of wave from what I guess I would call the baseline or the midline. So, I will draw a transverse wave to demonstrate this. I'm going to draw it over here. Here's a nice transverse wave. Okay. Now, the amplitude, if you imagine this being kind of the midpoint of the wave or the baseline or whatever you want to call it, then this, let's move it down a little bit, right here is the amplitude. That right there is the amplitude. The amplitude of a wave corresponds to something that we call the intensity of the wave. And you can actually measure intensity. We will not get into it in this class, but I remember in, I think, my second semester, freshman year of college, we talked about measuring wave intensity or light intensity. What this really translates to, when we talk about intensity, you have a very intense light wave. That means it's really bright. Okay. So bright light. A very intense sound wave would be a very loud sound wave. That is what the amplitude means. Do not get that confused with the energy. A louder sound wave does have a lot of energy. It doesn't quite work that way for light. I can't remember if we get, I don't think we get into that too much in this class. That's an AP Physics 2 or like a modern physics class. You did learn that last year though. You learned the relationship between energy and, you learned how to tell how much energy a light wave has. But we're not even going to get close to talking about that. All right, the wavelength. Wavelength is the, well, length in space, so a physical length of one complete wave cycle. Okay, so if I were drawing the wavelength, if I wanted to say what the wavelength of this wave is right here, I could say, okay, here's one crest, here's another crest. This is a wavelength. It is the physical length in meters or centimeters or inches or feet or whatever you want to call it of one wave. Okay? One complete cycle of wave. Wave cycle starts at peak or crest, down through the midpoint to trough, back up to crest. That is one cycle. Or you could go trough to trough. Or you could go midpoint to midpoint, but you have to be careful that the wave is trending in the same direction both times. Here to here, even though it's midpoint to midpoint, here your wave is going up, here your wave is going down. That's only half a wavelength. It would have to be wave going up, both at the midpoint. That is a full wavelength. Okay? Doesn't matter where you draw it, as long as it's one complete wave cycle. Frequency, is related to that, but it is not a measurement of space, it is a measurement of time. Okay? Frequency is I have the wrong definition on here. That's kind of funny. Frequency is, let's see, how do I want to fix this? The amount of wave cycles per time period. And the time period we usually measure in is seconds. Okay, that is what frequency is, the amount of wave cycles per time period. I have another definition here, and maybe I will, maybe I'll just put an arrow and say that this frequency is the inverse of period. And what a period is, as I hope you know by this point, a period is the time duration. Or I hope this at least makes sense to you. The time duration of one complete wave cycle. Period is the time duration of one complete wave cycle. So actually, if we go back over to our picture here, this is a picture. This, we don't have any labels on this. We don't know whether this wave is getting graphed in terms of, is this distance here? If it's distance, then this could be a wavelength. If this x-axis that we're graphing this wave on is a time axis, so in other words, this is as time goes on, we could call this the period. Okay, so whether this is the wavelength or the period depends on if we're graphing, if this x-axis represents space or represents time. It sounds really weird, but just stop and think about it. Like, if this is a distance axis, it's a wavelength. If this is a wavelength. If this is a time axis, this is a period. Time for one complete cycle to happen. Let's talk about what frequency is related to for sound waves and light waves. So the frequency of a certain sound determines pitch. We'll see this in a little demonstration later on. On the other hand, the frequency of light wave determines one of two things. We'll say it determines either the type of wave or it determines the color, if we're talking about visible light. Okay, just to separate those. Sorry, I'm kind of running into some other spaces here. Okay. Frequency determines the color of a light wave, which is crazy to think about. That was kind of what I was talking about in the last video. The color of something is dependent on how frequently, how many times per second the electric and magnetic field oscillate as the light is bouncing off of that thing. That's nuts. That's crazy. Okay, speed. You guys know the definition of speed? Okay, so you know its distance over time. I'm going to relate that a little bit more specifically to waves. The speed of a wave, we can talk about how fast a wave travels, is constant for a given medium. And again, medium just means material. It is a constant for a given material. Let's talk about how light, again, sound waves and light waves, that's what we're mainly going to focus on. How do sound waves and light waves vary in this regard? The velocity of a sound wave is approximately 340 meters per second. And when I say approximately, this number varies, okay? It changes. It goes up for either denser materials or warmer air. So in other words, you guys have probably tried to talk underwater at some point in your childhood. It's very distorted when you talk underwater, but the sound actually travels faster. And the way I kind of picture it is air is not very dense. The particles are spread far apart. So it takes some time for those particles to kind of knock into other particles and keep the wave going. Water is very dense. The particles are much more tightly packed together. It's a liquid, so it's not super tightly packed. It's not solid. But the particles are more tightly packed together. It's easier to get the particles to hit other particles and start that wave, start that pressure wave. So it goes up for denser materials, and that makes sense for why it goes up for warmer air as well. Warmer air, the particles are moving around faster. They can go and affect other particles a lot quicker. So the velocity of sound goes up for denser materials, and warmer air goes down, therefore, for less dense materials and cooler air. Okay, so that's the velocity for the speed of sound. The speed of light, hopefully you remember the symbol from last year for the speed of light. It is c, and it's equal to 3 times 10 to the 8th meters per second. Nice round number. And if you remember anything from last year, we did some stuff with Snell's law. We did refractive indices. We're not going to do too much with that, I don't think. But basically, what it turned out to be a material with a higher refractive index, light traveled slower in that material. And generally, what that meant, it wasn't a perfect trend, but generally what that trend meant was a higher, a more dense material. Slowed light down more. Light did not travel as fast in denser materials. So this goes down for denser materials. And I'll put just a little arrow on this. And at this speed, 3 times 10 to the 8th, this is in a vacuum. Okay, 3 times 10 to the 8th is for in a vacuum. It actually turns out that the speed of light is almost 3 times 10 to the 8th for light traveling through air. Air acts very similar to a vacuum for light. It's a little tiny bit low. It's not quite 3 times 10 to the 8th. But for denser materials like water, glass, diamond, quartz, whatever, it goes down. Now, as far as the relationship between the speed, the frequency, and the wavelength is concerned, hopefully you remember this from last year. This is a pretty simple equation. You can almost kind of get it from the units. Oh, we never talked about the units for frequency. Oh, I guess we kind of did, but I really misstated it. What I meant was the amount of wavelengths per time period. I meant that we usually measure the time period as some, in seconds. I guess this was not a good way to write it. So here's what I'm going to do. You guys are going to hate me, but that's fine. I'm very used to that. The amount of wave cycles per second. I mean, you can also do the amount of wave cycles per minute or per hour or per day, but no one does that, okay? Amount of wave cycles per second, and then we'll just put in parentheses, the units are 1 over seconds or hertz, Hz. Hertz is spelled H-E-R-T-Z, but we just abbreviate it with Hz. It's called a hertz, okay? If you look at like a motor, it tells you how many times it turns over per second. It's listed in hertz, okay? Maybe it's not, but other things are listed in hertz. Now, as far as the relationship between those, we know that velocity has units of meters per second. We know wavelength has units of meters. We know that frequency has units of 1 over seconds, which is the same thing as hertz. So this equation, I think it makes a lot of sense. If you look at these units, you say, okay, well, all these are related somehow. They've got to be. Wavelength is in meters. Frequency is 1 over seconds. This is meters per second. Huh. If I take a meter and I multiply by 1 over seconds, then I get a meter per second. So it stands to reason that if you take the frequency, you multiply by the wavelength, you get the velocity. This is the relationship between these 3 quantities. Okay, and let's see here. Oh, I got a little bit of time still before it shuts off on me. So, the relationship between these. For a wave in a given medium, and we already kind of said this, V is constant. If you have a wave in some material, the speed does not change, regardless of what the frequency is, regardless of the wavelength. The speed is constant in a material. The material determines the speed. Okay? So, what this means is that if you have, we're talking mainly about light right now, but it could apply to anything. Light of different frequency has a different wavelength, but the same speed, same v. This makes sense. If this is constant for a certain material, if the frequency changes, that means this changes. If this is constant, these must be inversely related. If the frequency goes up, the wavelength goes down. The wavelength goes up, the frequency goes down. So for a wave in a given medium that's not changing medium, it's not going from water to air or crown glass to flint glass or whatever we studied last year. For a wave in a given medium, the velocity is constant. On the other hand, for a single wave traveling between media, or different media, media is the plural of medium,